The Ingalls building in Cincinnati changes that. Engineer Henry Hooper dreams of a monolithic building of concrete, a skyscraper 16 stories tall. But many engineers believe that a concrete tower 16 stories high will collapse under strong winds or even its own weight. When Hooper finishes his building, there are many skeptics.
There's one anecdote that says that a reporter actually stayed up all night waiting for the Ingalls building to collapse because he was so certain that it was going to. Needless to say, the reporter was disappointed in the end.
It is a towering success for its time. But at 180 feet, it is just one in a dizzying array of modern-day skyscrapers. More than a century later, the towering dream of Dubai aims to be over 10 times the size of the Ingalls building. Every morning, workers assemble in the garage of the building. Erecting this much concrete in the punishing heat of the Gulf requires serious manpower. But before workers can pour a drop, the perfect formula needs to be mixed at the batch plant. The first problem this leviathan from the desert faces is its own height. The taller a building, the more it flexes, increasing the likelihood that it could flex to the breaking point, a deadly proposition. Older skyscrapers like the Empire State are safe because they use massive steel beams and braces. But erecting a tower nearly twice as high requires a material with even greater shock-absorbing qualities.
If you take something like the Empire State Building and the wind blows on the Empire State Building, well, the wind creates pressure, which are going to try and bend the Empire State Building over. But as you go higher, imagine now going twice the height of the Empire State Building. The wind gets more surface to work on. Indeed, buildings collapse when the flex is so great that the weight of the building gets outside of its footprint and the building doesn't have strength enough to handle that. Down it comes.
Builders will need a formula that is almost as strong as cast iron, yet more resistant to damage due to vibrations from the wind. After extensive computer and wind tunnel testing, the architects behind the Burj Dubai will use a high-strength concrete formula. It contains slag, a byproduct of the steel industry, and microsilica, which gives the concrete added strength.
If you look at the microstructure of concrete, there are many, many spaces between the particles that are either hollow, so we call them pores, or they are filled with water. Microsilica plays the role of filling these pore spaces between, and therefore it makes concrete much more dense, more durable, and stronger.
And in order to make sure that the formula is consistent, Alam Feroz, quality control manager for the concrete of the Burj Dubai, routinely tests the concrete before it is used in the skyscraper.
I'll give you an example. It's like if you're giving a blood to a patient, so how important is the blood to be tested before you give to the patient? It's a big risk. So same is with the concrete. When it has been tested, I get confident that whatever I'm giving to the structure is being tested and it complies to the requirements. It won't be just a mere guess.
To test the strength of the concrete, small cubes are hardened in cool water. Next, the concrete is deposited into a crusher for a stress test. This cube holds up to nearly 14,000 pounds per square inch, making it a high-strength concrete. The concrete test has been successful. But as strong as this formula is, it still has to contend with desert heat. Temperatures top 120 degrees. How do you keep concrete cool in the desert? Builders use a deceptively simple technique. Shaved ice. While it's being mixed at the batch plant, slices of ice are mixed into the concrete so that it remains cool inside of the mix trucks. When it arrives at the building site, the melted ice has kept the concrete from overheating. But now, the concrete has to travel hundreds of feet into the air.
The key technical problem for building a building of this size and of this height is going to be to vertically pump concrete of the order of 2,000 feet high. It takes huge amounts of pressure.
Mixer trucks deliver the mix to the pumps. The building requires 3 pumping stations where the liquid concrete is poured. The high-pressure pumps force the concrete through a complex system of pipes.
Now, the technology to do so is awesome. If you think in terms of water, you have 1,000 feet of hydraulic water pressure. That's a tremendous kind of pressure. Now, concrete weighs 2.5 times as much as water. So you need a piping system that's so much stronger, and also pumps that are so much more efficient to pump concrete up that high.
As the sun sets, the second shift workers return to feed this growing skyscraper. The concrete pour takes place at night so that the concrete can harden evenly.
At the moment, even though it's 10 o'clock at night, it's about 100 degrees Fahrenheit, and the humidity is about 90%. The advantage of pouring concrete in these conditions, because the humidity is so high, we don't have a problem with it drying out the top surface of the concrete, but we've got effectively another roughly 130 stories to go.
As the pour continues into the night, the Burj Dubai has reached a milestone. 25% of the building is done. When completed, this megastructure will stand over 2,000 feet tall, making it twice as high as the Empire State. It will be covered in a reflective glaze to protect it from the extreme heat and high winds of the Gulf. But the building's guts are solidly concrete. When it's finished in 2008, the Burj Dubai will be the tallest building in the world. Like the Ingalls, the Burj Dubai has set the standard for its day, showing once again that concrete can be used in a variety of ways for the world's tallest buildings. Now, reinforced concrete is establishing itself as a building material of choice for skyscrapers. Concrete has conquered the skies. Concrete's next quest, how to tackle the building challenges of the future. Concrete has been a key ingredient in the construction of our civilization. It has been a fundamental part of our architectural past and is now paving the road for our future. Scientists are developing new formulas for concrete and are looking for ways to make it stronger, more environmentally friendly, and capable of doing things we never thought possible. Back where it all started, at the heart of the Roman Empire, concrete has taken a new and exciting turn. Just a few miles from the Pantheon, the Jubilee Church, designed by architect Richard Meyer, uses a new form of concrete. The church was commissioned by the Archdiocese of Rome to commemorate 2,000 years of Christianity. For that, the building would need a material that was both ancient and modern, a material that would speak to the church's past and make a bold statement for the future. They would also need a material that would last the test of time. Concrete fits the bill.
This church is remarkable for several reasons. It has these 3 sail-like forms, loosely representing the Holy Trinity, but made in effect of giant concrete blocks.
The shells of the church, which stretch out and up in the same way as the Sydney Opera House, are made of 346 white, reinforced, precast concrete blocks.
Concrete, for all of its advantages, does tend to pick up discolorations from the atmosphere and so on. Meyer, though, wanting to keep his building white, managed to work with local firms in order to achieve this concrete mix that included these photocatalytic particles that will absorb and neutralize the acids in the air. And in effect, what you'll have is a pollution-eating building.
Italcementi came up with a revolutionary new formula for the concrete that will keep it as pristine in 50 years as it was on opening day. All concrete structures tend to stain and degrade from pollution. Over time, this has given concrete a bad reputation. But the unique formula for the Jubilee Church contains a secret weapon: photocatalytic particles.
Now, in effect, what these do, when activated by the light of the sun, they mix with the acids in the air and neutralize those acids, neutralize the discoloration that would come typically from atmospheric pollutants. So, in a way, you kind of have a self-cleaning building.
This test demonstrates the photocatalytic particles at work. The concrete neutralizes pollutants, allowing it to maintain its brightness and not degrade over time. It is a revolutionary new development that has the potential to transform the way we look at concrete forever. Concrete isn't just working harder, it's working smarter. New developments in concrete technology now allow for what used to be unthinkable: helping the environment by using an unusual aggregate: glass.
The innovation here has been in making sure that the glass doesn't get corroded by the lime in the cement mixture. One of the biggest issues with concrete is that the Portland cement tends to be quite corrosive, and this has been a big problem with things like recycled glass. It tends to corrode the glass falls out. This composition of cement was actually developed by Columbia University. It is a much less corrosive, more benign cement, allowing you to put the glass chips in. So you can actually now have concrete with glass chips that actually has a good surface effect.
We are generating millions of tons of garbage, solid waste, and in New York City, approximately 6% of all solid waste is glass. That's bottles like this, yeah. And these bottles generally find their way into landfills, and that costs taxpayers hundreds of millions of dollars just to get rid of these bottles.
Concrete's versatility allows it to bind with other materials, in this case, glass. The first step is to separate the bottles by color.
And then you crush them in a crusher. Now, crushed glass is not something like this. This is what we call broken glass, and that is something you want to handle very carefully. It has sharp edges, and that was also one of the problems we were facing, because skeptics asked, well, if you use glass in concrete, won't people cut their hands by handling the blocks or whatever? Answer is no, because when you crush the bottles in a high-impact crusher, it comes out in pieces like that, and it's just like sand. It does not have sharp edges.
Eventually, the broken glass is crushed into a fine powder.
So this is just like powder, like baby powder, the same kind of particle sizes. So if you put this finely ground glass powder into concrete, you can replace part of the cement by this glass.
These are actually 100% recycled glass pieces added into the concrete.
Initially, scientists thought that recycled glass would make for a bad aggregate. But Professor Meyer and his team have found a way.
Okay, so once you make concrete out of these glass particles and color coordinate that very well, then you can get something like this, and this is now already being commercially produced. Now that's the way how regular concrete would look. And this is here our glass concrete, polished to a high precision, high grade of polishing. And that is known as terrazzo concrete.
Using recycled glass as an aggregate is just one of the many ways that concrete continues to reinvent itself. It also may pave the future for a more environmentally friendly concrete. There are also other developments reshaping concrete for the future. For the last 100 years, architects and builders have sought a way to allow light into concrete buildings, homes, and offices in a more efficient manner. One of concrete's biggest drawbacks is that it creates dark buildings that do not effectively conduct light. Experts are working to change this.
Okay, this is a piece of light transmitting concrete. It seems like an odd concept, but what they've done here is to take standard concrete and add glass fibers. Okay, so what you're seeing here is the blue LED passing through the glass fibers that are embedded in the concrete.
Imagine concrete allowing light to